So this week we're really excited to have Erkao Bao. He's going to be discussing applications of obstruction bundle gluing on the definition of cylindrical contact homology in dimension 3.
Thank you for the, can you hear me? Okay. Thank you for the organizers. It's my pleasure to give a talk here. So first, let's go to the setup. V Kasai is a closed contact manifold, and alpha is a contact one form, and R is a Riemann vector field. So we make some assumptions. First, we assume alpha is non-degenerate. Roughly means there's no infinitesimal deformation for all the Riemann bits. And also we assume there's no contractible Riemann bits. So then let J be an alpha tame, almost a complex structure on R times the contact manifold with S is the R coordinates. And by alpha tame, we mean slightly different. So these are explained in Russell's talk. So I just quickly remind you what they are. So we require that J is R invariant, and J maps the ds to G to a function, positive function on V times the Riemann vector field, and J preserves some two-plane distribution and psi prime such that d alpha VJV is positive if V lies in non-zero and inside the psi prime. And let me also remind you the elimination of elliptic orbit. So given L and epsilon greater than 0, there is this a positive function on V such that phi on V such that phi is epsilon close to 1 in C1 norm. And the phi, if you use a phi to modify the contact form alpha, so phi alpha has no elliptic orbit of action less than L. And also phi times alpha is L simple, which I will also remind you in the next slides. And the advantage of being elimination of elliptic orbits is because if gamma is a hyperbolic orbit, then the Conley-Zander index of gamma to the power k equals k times the Conley-Zander index of gamma. And this implies if no elliptic orbits, let's say V is a J-holomorphic curve converging to hyperbolic orbits, and V is a k-fold branch cover of another holomorphic curve U, then the Fredholm index of V equals k times the Fredholm index of U plus B, where B is a number of simple branch points. So this formula we'll use in a moment to show that d squared equals 0. Remind you the L simple quickly. So so a contact form is L simple if around each positive hyperbolic orbit. So for each positive hyperbolic orbit of action less than L, it has a neighborhood d squared cross the S1, and where with the coordinate x, y inside the disk, and the t is in the r in the S1 direction and inside V, such that the Riemann orbit is in the origin where x equals y equals 0, and the contact form looks like a constant plus a quadratic term plus the x dy minus y dx. And if it's negative hyperbolic, we actually make the coordinate x, y, t needs some identification like this. So x, y, t identified by minus x, minus y, and t plus 1. So then the almost a complex structure, the alpha tame almost a complex structure has the property that it maps the dx direction to dy, and it maps the dx to dy and the ds to s. Recall s is in the r direction, and it maps ds to dt plus the Hamiltonian vector field of q inside the disk, and so this thing is a constant multiple of the Rib vector field. Okay, so this is just some preparation. So now we move on to the definition of a cylindrical contact homology. So the chain complex is a Q module generated by all the good orbits of alpha. And then the differential D is defined over the generators by this formula. So it's a sum over all the Rib orbits or good Rib orbits. And we count the modular space of J holomorphic cylinders from gamma to gamma prime of Fredholm index 1, and so this one has a this is a one-dimensional modular space, and then you mod out the translation by R, and then so in good cases this is just a finite number, so you count the number, and this will be the coefficient in front of gamma prime, and you also need to multiply by 1 over the multiplicity of gamma prime, where so the multiplicity means if gamma prime is a k-fold cover of some simple orbits, so then the multiplicity is k. So here good Rib orbits mean so the some Rib orbits are good, some are bad. So bad if it's bad if in this special case if it's a even cover of a negative hyperbolic orbits, and so we need this for orientation purpose. So otherwise, so the modular space of homomorphic curves need to be coherently oriented, and so but I don't want to go there. And so the main result we want to cover today is this theorem. Suppose alpha is non-degenerate and has no contractible Rib orbits, then the cylindrical contact homology is well defined, and it is also an invariant of the contact structure, so in particular it's independent of the contact form we choose, and also independent of the almost a complex structure we choose. So I would only give so there's a bunch of related work there under. So the conditions are different, and the results are also different. Approach are also different. So Hutchins, Nelson, Pardon, and another paper of Hutchins, Nelson, and Ishikawa. Okay, so let's go to the rough. Let's prove this theorem or schedule proof. So first, let's look at the d squared equals 0. So d squared equals 0 roughly because there's no elliptic orbit. So for example, let me draw a picture. So to show d squared equals 0 inside the inside the simplexization, we look at holomorphic curves. Sorry, my hand is a little cold, so I shake a little. So inside simplexization, you look at the holomorphic curves of index 2, and then you want to see how this degenerate. And if this degenerate into into a holomorphic building of index 1 and index 1, then so this is a D and the D. So D squared is the boundary of a one-dimensional manifold. So you can show D squared equals 0. So there a priori it's possible that this can degenerate into a multiple level of a holomorphic building. Let's say U1, U2, sorry. Let me order it, U3, U2, and U1. And let's say a multi-level and not necessarily third level. So let's say UI is a KI for the cover of VI. So because J is a generic, so VI is there. So this requires by the previous formula we have a index of UI equals KI times index of VI plus let's say branch points BI, which is also positive, negative, and so because the index of VI has to be greater than 1, so therefore this is great index of UI is greater than 1. So therefore, for each piece has a Fredholm index greater than 1. So therefore you can see there's only 2 levels. So yeah. So in this case, the D squared equals 0 is it's easier to prove. So because of this formula, this formula, and then so we have D squared equal to 0. Then next we need to show that an exact symplectic cobordism gives a chain map. So this one also requires uses a no elliptic orbit, and also it uses a little bit of automatic transversality. So I don't want to go to the proof there. So let's just because I want to move to the obstruction bundle gluing. So let's take it, and then finally we want to show the chain homotopy. To show chain homotopy, so roughly we want to show that a family of exact symplectic cobordism, W tau, alpha tau, J tau, where tau lies in from 0 to 1, gives a chain homotopy, means phi 0 minus phi 1 equals KD minus DK. So for some linear map K. So to prove this, we need to do some obstruction bundle gluing. So for the rest of the talk, I will just focus on how to do the chain homotopy part. So to get a chain homotopy in general, I mean, usually one look at the modular space of J tau holomorphic curves as tau of Fredholm inside the symplectic cobordism of Fredholm index 0, connecting from gamma to gamma prime, and tau lies in this one parameter family. And we want to study the boundary component of this one-dimensional modular space. And of course, when tau equals 0, we get the phi 0, and when tau equals 1, we get phi 1. So now we want to see other boundary component that will contribute to the right-hand side of this equation. And one possible degeneration is illustrated in this picture. So you look at the index 0 curves, index 0 cylinders inside the cobordism, and from gamma to gamma prime, and it can break into a holomorphic building of level 2. And the top part is we denote by V plus. It has a Fredholm index K for some positive integer K, and the lower one is a lower one we denote by V minus. It's of a Fredholm index minus K. And let's say K is some positive integer, and so we assume further that gamma and the gamma. So we assume further that the gamma and the gamma prime means these two orbits are positive hyperbolic, and this one, the middle one, is negative hyperbolic. For the other case, one can do similar arguments, but the arguments. So yeah, so let's just stick to this case. Later on, I'll point out where the difference might be. So then, oops. Then this V minus is a k-fold cover of a simple curve U minus, and let's assume U minus is transversely cut out in the family. So the V minus has a index minus K, and the U minus has index -1. So for a generic J, so this kind of curve appear, and by automatic transversality, you can also show that the kernel of U minus is 0-dimensional, while the co-kernel is 1-dimensional. Well, for V minus, the kernel is also 0-dimensional, while the co-kernel has dimension K. So that yeah, so that follows from automatic transversality.
Wait, I thought U minus was transversely cut out. How could it have co-kernel?
Oh, so U minus is a so for this, it's transversely cut out in one parameter family. So
I see.
So yeah, itself is, yeah. So yeah, so it has a 1-dimensional co-kernel, which should cancel out with a variation of the almost a the variation of this family. So yeah, so this is a so for U minus, this is the same phenomena. You see the same phenomena in Morse homology. If you try to show the Morse homology is independent of some Morse function, and you do have a if you look at one parameter family of Morse trajectories, then you see some Morse trajectory increase the index. Yeah. So, but so for U minus, that's so for generic J, so that's expected. But because of the homomorphic curve, because we here allow multiple covers, since the U minus is there, then V minus is also there. So that's so I mean, if K equals 1, then this is exactly what we want. So because the upper one will be D, and the lower one will be the chain homotopy K, and then that's exactly what we want. But because of V minus can be a multiple cover U minus, so then we need to study this situation. And roughly, so there are discretely many V minus, but over this modular space, this is a k-dimensional or k-1-dimensional modular space. You model the translation, and among this modular space, there's only finitely many of V plus that together with V minus will be able to serve as the boundary of this 1-dimensional manifold. So our goal is to figure out among this among this large modular space, which of these V plus can be glued to this V minus. So let's move on to. So then this is a obstruction bundle gluing. So let's say let M be the modular space of V plus, just in picture, modular space of holomorphic curves of index K, holomorphic cylinders of index K connecting from gamma to gamma double prime. And then by Hutchins-Taub's gluing tool, there is a obstruction bundle O over the modular space M quotient out by the translation. And the fiber over V plus is the co-kernel, but I write it as the co-kernel V minus, but it's isomorphic to the kernel of V minus, co-kernel of the, sorry, dV minus is the linearized a normal d-bar operator, and it should be the co-kernel, but it's isomorphic to the kernel of the adjoint operator. And there's a slightly variation, a slightly difference is inside this space. This is a k-dimensional vector space. There is a special one-dimensional space. I denote spanned by a vector v. A vector y. So I denote by r of y. So we need to quotient out that one-dimensional space. So this y comes from the variation of the almost a complex structure. So roughly it's I mean, if you write down the d-bar equation, then you can see there's a term relates to the derivative of the so there's a term that differentiates the complex structure in the tau direction. And so then we take the dual of this, then we take the dual of this vector space. But anyway, so this bundle is a trivial bundle. And also we have a section S of this bundle. And so this is the obstruction section, such that the zero of this section corresponds to the curves inside this modular space that are gluable to V minus. So that's so we want to understand what are the zeros. And okay, so to understand the obstruction section, first let me introduce the notion of a evaluation map. So let's say alpha j is a L simple. So alpha j L simple implies that the d-bar equation is linear near the Rib orbits. So that means, let's say for V plus inside the modular space, near the negative end, where it converges to gamma double prime, we can write the V plus into V plus st equals st and eta plus st. So where s is the r times v, the r direction, and the t is the Rib direction. So we actually use the coordinate in the st in the target to parameterize the domain. And then the eta plus, so this this part satisfies this equation. So this is a J-holomorphic curve equation. So it just boils down to this. So DDS of eta plus minus A times eta plus equals 0, where A is the asymptotic operator at gamma minus. So so in other, if we didn't choose alpha j to be simple or L simple, then there are additional error terms. But in this case, there are no error terms, just this linear equation. And then from this, one can easily solve that eta plus can equals equals a formula like this, where Ci is some constant times e to the lambda I times s times fi of t, where lambda I and fi are eigenvalues and eigenvectors of the asymptotic operator A. And we arrange the eigen, so these are, A is a self-adjoint operator. So then the eigenvalues are real, so we all order them in this way. And near the negative infinity, so S is negative, so we want to make sure this lies in the whatever sublift space, L2 space, for example, and then we require the lambda has to be positive. So then the evaluation map is defined as follows. From the modular space to Rk is given by just those coefficients, C1 through Ck. And then one can prove that for a generic J, the evaluation map misses the origin of Rk. And hence you can remove the origin, and then in the domain there's a translation, so it induces a map on the quotient like this. So you quotient R from domain, and in the target you remove the origin, and then you quotient out the R plus action. So it's easier to, it's actually not hard to figure out the R plus action if you translate the curve eta plus. So you translate in the S direction, so you just change the power S plus S0, and then you add up by multiplying e to the lambda S0. So the R plus action on this is just you multiply by e to the lambda 1 and e to the lambda 2. That's how the R plus action acts. And then you quotient out the R plus action. It's a diffeomorphic to a sphere of dimension s-1. So, and also for generic J, you can show that the evaluation map actually is transverse to the north pole and the south pole. So now let's do the chain homotopy part. So first, the proposition is the pre-image, the count of the pre-image of the north pole and the south pole under the evaluation map is same as the count of zeros of the obstruction section. So this is a signed count. And so assuming this is the case, let's finish the proof of chain homotopy. So to show chain homotopy, we already know that, so we only look at, we only care about the pre-image of the north pole and the south pole and inside the sphere. And then we actually choose a generic path inside the sphere connecting the north pole to the south pole. And then we look at the pre-image of this path, so inside the modular space. So this is a one-dimensional manifold. And it may have additional boundary components, consists of consists of two-level holomorphic building of the form U plus and U minus, where U plus has index 1 and U minus has index k minus 1. And so then you can see this index 1. So this is all the curve here, they are in the simplexization. So so then the U plus is like the differential, the D, and the U minus contributes to the chain homotopy K. So these two terms gives KD in this formula. So let me draw a picture. So inside the sphere, you have the north pole and the south pole. and then you choose a generic path new, and that connects them, and you look at the pre-image of new under the evaluation map. And so you may wonder that so here it says I mean, if there's no additional boundary component, that means all the zeros, they cancel out. So that's even better. So there's a phi 0 minus phi 1 equals 0. So that's also good. But there might be additional boundary components, and the boundary components you a priori is, so there is one may wonder that there may be a holomorphic two-level building, like so this is gamma double prime, and this is gamma, and in this picture you have a U plus and U minus, and so this whole thing is inside the simplexization, and this one has index 1 and this one has index k minus 1. So things like this, they do not show up. So I'm drawing things that do not show up. So this is index 2 and this index k minus 2. So this is because we are looking at the pre-image under we look at the map under the evaluation map. The evaluation map only, so here the evaluation map is evaluated along the negative ends. So this piece is so this is a codimension 1 boundary. So this is a codimension 2 boundary, because the evaluation map doesn't see this piece, only sees the lower piece. So generically, for a generic path, you only get this copy, and so that's all we need for the chain homotopy. Okay, so now we'll spend the rest of the talk proving this proposition. So the count of zeros of the obstruction section is same as the count of pre-image of the North Pole and the South Pole under the evaluation map. So that's finally we move on to the obstruction bundle gluing. So V plus is, so recall that we have a V plus in the, simplexization and V minus in the cobordism. So this is, and so now we glue. So to glue them, we first do a pre-gluing. We get V star. So the pre-gluing, actually, there's a it's also a little bit the choice of the way it's explained in earlier lectures, so but I just want to say it again. So this is V plus, and this is a V minus, and then one use the cutoff function beta plus like this. So this is a 1, this is a 0, and another cutoff function. So sorry. So this is a cutoff function beta plus, and there's another cutoff function beta minus, which is beta minus is like this, and they overlap. So there's some overlap. And so that's the way one do the pre-gluing and get V plus. And when we have the V plus, we perturb V plus again using the sections psi plus and psi minus. So psi plus minus are normal sections sections of the normal bundle V plus and V minus, namely. So you can view. So here we choose a small perturbation psi plus, and in the bottom we choose a perturbation psi minus. So then we solve this. Then we get our candidate V. We try to solve d bar V equals 0, and it's explained many times. This can be rewritten as the sum of two equations: beta minus times theta minus plus beta plus times theta plus equals 0. And we actually require theta plus and theta minus to both 0. So where theta plus is this equation, so that's the linearized d bar times d bar. D plus is the linearized d bar of V plus and times plus psi plus the contribution of eta minus, which is comes from this piece, and so that because that's a derivative of beta minus, which only supported around here, and plus some junk term, and theta minus is a similar equation, but there's an additional term which comes in this. We are doing the chain homotopy, so there's an additional term comes from the variation of the complex structure, almost a complex structure. So let's denote it by. So we are solving the equation at the. We are trying to do J tau holomorphic, and let's say the breaking is at tau 0. So we try to solve d bar of. So we try to d bar of J tau equals 0. And then we assume that the breaking happens at tau equals tau 0. So the first equation is nice because d bar is transverse. So this one you can solve. You set it equals 0, you can solve it. The second one you cannot always solve it. So what we'll do is we solve as much as possible. So the y, we rewrite this y prime as the sum of two parts. One lies in the image of d bar. So sorry, image of linearized d bar. So this is the part that we can solve, and another part we denote by y, which is in the which is perpendicular to the image. So I write it as a kernel of the adjoint operator. So, and then we denote zeta to be this term. So we decompose y prime, and then we also decompose this term. So this one we decompose it into 3 pieces. One piece, as usual, is the image. Another piece is actually in the span of the y here, and then the rest of the term we denote by zeta 3. So instead of solving theta minus equals 0, we solve these 3 equations. And the first equation is nice because the y prime and the z1, they all lies in the image, so you can solve it. And the second equation, you can also solve it because zeta2 lies in the image of y. So this gives some uniquely determines the tau. So that's can also be solved. And so what's left is that 3 terms. So you want to solve this, but this one is not always solvable. So this will be the obstruction section. So let's so let's denote the obstruction section on the V plus to be an element inside here. So it's for any sigma lies in this space. So obstruction section is the dual of this vector space. So for any element sigma inside this vector space, we take L2 inner product with the Z3, which in the previous slides, and in other words, so if I copy it, so this is just this term. So that's the obstruction section, and the lemma is there is this. So now, so this is the obstruction section. Then we'll move as Michael explained. We also want to construct the linearized section. So that's the next thing I will do. First, I will. The lemma says there is this a basis sigma 1 sigma k for the kernel of the adjoint d bar operator, and so this is a k-dimensional, such that the positive end of these sigmas for I equals 1 through k minus 1 are of the form e to the minus lambda s times fi. So these are the eigenvalues and the eigenvectors again, modulo higher terms with a higher eigenvalue. And also we make sure that also sigma k equals y modulo higher term. So this y is exactly the variation of the complex structure. And this one, the proof of this lemma roughly goes like if you look sort of this is roughly just this roughly automatic transversality. So you look at the linearized d-bar operator, but instead of standard weighted stop-left space, you make the weight changes. So every time the weight hit an eigenvalue, the Fredholm index changes. But after it changes, you keep analyzing the kernel, and by automatic transversality, you see the kernel is still 0-dimensional. So each time the index actually goes from index, as you increase the weight that goes from index k to k minus 2, and then k, so the index decreases. The only reason index decreases if in this case would be you are adding co-kernel elements. And because you change the weight, you know the co-kernel elements you are adding are exactly of the form like this. So yeah, so that's the rough proof. And then, so then we define the linearized section as 0. So here it's X on the basis by this formula. So here I put a tilde over sigma I, where sigma I is the sigma I tilde is sigma I with all the higher terms truncated. You set them to 0. And also I throw away the garbage term. So this is the definition of a linearized section that we use. And so a straightforward calculation can show that this one this is actually straightforward. So then this is just equals e to the minus lambda t ci. So here I didn't quite explain what t is. So t is the gluing parameter. Yeah, but yeah. So t. So when you glue, you translate the curve. So that's the gluing parameter. Okay, so with this, so the linearized section has a really simple format. So then one can easily check that the zeros of the linearized section is same as the zeros of the North Pole and the South Pole under the evaluation map, because it's just CI. So then the final piece of thing that we need is the following lemma. We want to show that the number of zeros of the obstruction section is same as the number of zeros of the linearized section. So this one. So if we show this, then this will finish the proof of the proposition, because now the zeros of obstruction section, which are the curves that will glue to V minus, are exactly same as the pre-image of the North Pole and the South Pole, and yeah, so that will finish the proof of the proposition, and the proposition gives a chain homotopy. So to prove this lemma, one needs to find a homotopy to construct a straightforward homotopy between those two sections. Just interpolate, and then one need to show that during this homotopy, there's no zeros escape to the boundary, because the modular, even though it's a trivial bundle, but the modular space has boundaries. So yeah, and yeah, that's the reference. Okay, yeah, that's the end of talk.
Thanks so much, Erkao. Let's all thank Erkao. Right. Then, does anyone want to ask a question while they're being recorded? It always feels really stupid to ask that question. All right, I'm going to stop the recording.